Welcome to week 9. This week we're going to start talking about vector calculus by learning about divergence, curl, and vector fields. The part of physics that uses these topics the most is electricity and magnetism. So I want to motivate our discussion by first talking about Maxwell's equations. So Maxwell's equations are pretty famous. So you've probably seen them before. But do you know what they really say? So these are Maxwell's four equations. This symbol here means the divergence of the electric field. This is about the divergence of the magnetic field. This is about the curl of the electric field, and this is about the curl of the magnetic field. And these over here are partial derivatives rather than the derivatives we've been using so far. So by the end of today's video, you should be able to read these equations and know what they mean. Although we'll spend basically the entire course of electricity and magnetism learning how to use the equations. But to start off with, I just want to introduce multivariable functions and partial derivatives. So far we've been looking at functions that only have one variable, x or t. When we're looking at multivariable functions, they're functions of x, y, and z, sometimes x, y, z, and t. So we need to make sure we know how to label our derivatives in that sort of situation. So instead of writing the derivative with respect to x, you can write, so these are called partial derivatives. It's really important when you have a function of multiple variables that you specify which variable you're taking the derivative with respect to. And when you're doing that, you just use this delta instead of this d. So we have del dx, del dy, del dz, del dt. So the letter tells you which derivative to take, and you leave the other variables alone and treat them as constants when you're taking those derivatives. Let's look at an example. Okay, so here we have a function where x, y, and z are all variables. So if you take the derivative of this function with respect to x, then x is your only variable and you treat y and z as constants. If you take the derivative with respect to y, then x and z are constants and y is your only variable. And if you take your derivative with respect to z, then x and y are constants. Okay, so it's nothing terribly difficult. It's just a matter of remembering to sometimes treat variables as constants. So I'll give you a few just to try for yourself. Okay, so I've given you a multivariable function and I want you to find each of its partial derivatives. So pause the video and give it a go. Alright, so if x is our variable, then we just get e to the y sine z. If y is our variable, well, the derivative of e to the y is still e to the y. So nothing changes in this case. And in the last one, if z is our variable, okay, pretty straightforward. So these are the partial derivatives. But there's another type of derivative you can take of a scalar function, and that's called the gradient, and that's what I want to talk about next. Okay, so the gradient is a vector form of a derivative. You can think of it as the total derivative of a multivariable function. So think of your multivariable function as a topographical map. Just think of it as a two-dimensional function of x and y. So this one here, for example, if we just ignore the arrows, the dark spot in the middle is the top of the hill, and then the light spot is out here, our lower values of the function, so our function is really representing a hill. And so our gradient is pointing up the hill in the direction of steepest descent, so our gradient is a vector, and so that's always pointing up the hill. And the size of that vector, the magnitude of the vector, is determined by how steep that descent is. Now look at this one on the right. Here our multivariable function is largest on the left side and smallest on the right side, this is really just a ramp. So our gradient, which is our vector that always points up the hill, is pointing in the same direction everywhere. And again, the size of it is determined by how steep that ramp is. Okay, I thought it would be good to use some pictures from the computer because I can't draw shading very well. Okay, let's look at our formal definition of the gradient. So if we call our scalar function, here I'm just going to start using t for our scalar function. So this is a function like f of x, y, z. I'm just changing the letter to t. So the gradient of this function is the derivative of t with respect to x, x hat, plus the derivative of t with respect to y, y hat, plus the derivative of t with respect to z, z hat. So the x component is the derivative with respect to x. The y component is the derivative with respect to y, and the z component is the derivative with respect to z. Okay, let's look at an example. And the first example I'm going to pick is going to be easy to calculate, and the reason I picked this one is because it's easier to visualize than something a little more complicated. And I really want you to get conceptually what the gradient means. So here I just have a function. It's really just a function of x, not of y and z, but we can still draw it as though it's a function in multiple dimensions. So the gradient of this, alright, so this gives us 2x x hat, and here x is a constant for this here. When you take the derivative with respect to y, you get 0. When you take the derivative with respect to z, you get 0. So our gradient is just 2x x hat. Now I want to think about what this really looks like, and bear with me as I attempt to draw this. Yes, I could get computers to draw this nicely, but I want you to be able to do sketches as well. I'm going to draw this as a topographical map. Remember, this means that when the lines get closer together, it's getting steeper. And just pretend this is symmetric. Okay, so we have a function that we know is 0 along the y-axis. And as we get further away from the y-axis, the function gets larger and larger, and the slope gets higher and higher, right? Because in profile it looks like this, approximately. What's our gradient look like? So when x is positive, it points to the right in the positive x hat direction. When x is negative, it points in the negative x hat direction. And the further away from x equals 0 you get, the larger it gets. So you see that the gradient is always pointing up the slope, and that it gets larger when the slope gets steeper. Yes, I know my drawings aren't perfect. Far from it. Use your imaginations. Let me know if that makes sense. I'm going to give you some gradients to calculate yourself. Sometimes they're easy to calculate but hard to visualize, but if you think you can visualize it, go ahead and try to think about a topographical map and what that gradient really means, because I really want to make sure you understand what a gradient means conceptually. So go ahead and calculate the gradient for each of these functions. And for the first one, you should be able to visualize it. The second and third one are harder to visualize. Okay, so this first one, first we take the derivative of x plus y with respect to x. That gives us 1. So we just get x hat. When we take the derivative with respect to y, we also just get 1. So that's y hat. It's not really a function of z, so the derivative with respect to z is 0. So we just get x hat plus y hat. So it's a vector that always points in this direction. And really, if you think about this function, it's a ramp that's sloped up this way. So that does make sense if you can visualize it. Alright, this next one. So the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. Okay, pretty straightforward to calculate, but I wouldn't try to visualize this one without some computer tools. Okay, last one. The derivative with respect to x is just e to the x. So this term is just a constant, and the derivative of a constant is 0. Alright, then we do with respect to y, and then we just get left with sine z y hat. So again, e to the x in this case is just a constant, and so sine z. Alright, last one with respect to z, we just get y cosine z. So I have had students before, they know how to take derivatives like this, but when they have to sometimes treat certain variables as constants, they get kind of mixed up. So let me know if you have any issues with that, but I think with practice, you'll just get used to it and it'll be alright. We've been looking at scalar functions of multiple variables. Now I want to look at vector functions of multiple variables, which we also call vector fields. So this is when your function is actually a vector, so your function has a value, a magnitude, at all points in space, but it also has a direction. And where we're going to use this the most is when we are learning about electric fields and magnetic fields. Again, this part of math is most relevant to E&M. I'm just going to write this in a little bit different form. So a lot of times vector fields are written with the letter V, sometimes they're written as a capital F, so I'm going to do it both ways just so you're used to using it both ways. And I'm just breaking this down so you think a little bit harder about what this means. So we have a function that has an x component, a y component, and a z component. And each of those functions is a function of x, y, and z. And also sometimes t, or time. Okay, now the best way to get a feel for these is to draw pictures. Alright, let's start with something simple, where our vector field is just 2x hat. So it's a constant that always points in the x hat direction. Let's look at how this looks. Now, while these things can in principle be three-dimensional, and they often are, for the purposes of learning to visualize them, we're going to stick to 2 dimensions. Stop and think for a minute. What do you think this should look like? This is a vector that is always too long and always points in the x-hat direction. So no matter where we are in space, it just looks like this. Now, part of the reason I'm hand drawing these and not using a nice computer tool to make this look beautiful for you is because I want you to be able to sketch these yourself. So to learn to do this yourself, I want you to see me drawing them as well. So, like on your homework, for example, I will ask you to sketch vector fields, and I want you to know your drawings don't need to be perfect. They can look like mine. So basically what I've drawn is a vector field where the vector is the same everywhere. That's all this one is. Okay, so that's a simple example. I'm going to show you a couple examples actually. Alright, let's look at another one. So think about what this one should look like. And if you're having trouble thinking about it, you can always plug in values for a couple points. Like you can say, well, at y equals 0, this is 0. So everywhere where y is 0, this function is 0. When y is 1, it's just y hat. You know, you can plug in the values and think about it. Right? At y equals 0, so along the x-axis, this function is 0. So there's no arrows coming there. get to y equals 1, it's just y hat. Well, y squared is also 1 at minus 1, so it's also going to look like this down here. These arrows should all in principle be the same length, but when you're sketching, you don't have to be super perfect. Okay, when y equals 2, now it's at 4, so it should be twice as long. And don't worry about drawing arrows at the exact point or getting the size just right. You just want to get a feel for what they look like. Okay. Alright, let's do one more example. Okay, this one's a constant again. So no matter where you are, this vector field has the same value. X hat plus y hat looks like this. So no matter where you are, you see this. Okay, so I hope that gives you some general idea. And, it's up to you to decide when I ask you to sketch how many of these arrows you want to draw. You just want to draw enough arrows to show the general trends or patterns in the function. Now I'm going to give you a couple to draw yourself. Again, I'm sticking to two-dimensional functions, even though you can do this in 3 dimensions, because, well, 3-dimensional drawings are rough. Alright, so pause the video and sketch your drawings. Okay, so this one always points in the y hat direction, and the magnitude of it depends on the value of x. So that means when x is 0, it's 0. When x is 1, it's 1. So we'll draw some short arrows here. And this is also true of minus 1. At x equals 2, well now, they should be 4 long. Then, you get to x equals 3. Well goodness, I don't really have room to draw this properly. But you get the general idea. We are just sketching, so it doesn't have to be perfect. Just give you some idea of what's going on. Okay, next one. Alright, this one always points in the x hat direction. When x is positive, it's positive. When x is negative, it points in the negative direction. And it gets bigger the further away from the y-axis you get. I'm not being super exact. I'm just showing the general trends. Okay, last one. So this one, it can get a little confusing to think about, so you can always plug in values. You can say, alright, at the point x equals 1, y equals 0, it goes this way. You can just plug in values as you go around. And you'll figure out it goes around this way. And x and y get bigger as you get further away from the origin, so the arrows get bigger. Imagine that goes along the axis. Okay, so this one you can see it all spreads out from the center. Alright, I hope that makes sense. And really it just takes more practice to get used to drawing these. And again, when we actually work with this, we're going to be working with electric fields and magnetic fields. That's what this really comes down to. Now, when we're looking at vector functions and multiple variables, we can't use the gradient because that's for a scalar function. We can't use regular derivatives. There are 2 types of operations that are kind of like derivatives that we can use in this situation, and we're going to talk about those next. So the first operation we're going to talk about is called divergence. And divergence you can see in this vector field here, and also in the last vector field we just drew. So divergence is a measure of how much a vector field shows something spreading out. So if you think about it in an analogy of water, you have a source of positive divergence if you drop something in water and it spreads out. If we come back to E&M, where we're going to be using this a lot, a positive charge is a source of divergence in electric fields, and negative charge is a source of negative divergence in electric fields. So let's look at how we find divergence. Now, divergence is actually a scalar quantity. And to think about it, it's going to help to think about this del operator as a vector. It is not technically a vector, it is an operator, but we can still think about it as a vector just to help us remember what it is. Okay, divergence is the dot product of this operator with our field. At this point, I'm going to go back to representing our vector fields using the letter V rather than the letter F. I go back and forth. I just want you to feel comfortable going back and forth as well. So V is our vector field. Divergence is the dot product of this operator with that field. So what does that actually look like? So let's write out what this is. So the divergence of V is the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. Remember, the dot product is a scalar, divergence is a scalar. So let's look at an example. We're starting with a simple example so we can visualize it. So the divergence of V, well, it has no x component, it has no z component, so we just have to worry about this term. So the derivative of the y component with respect to y is just 2y. That's all it is. So that's a scalar. So let's visualize this. Oh, that's coming out nicer now. Okay, so this is a function that gets bigger as y gets bigger. Now, I rarely get these things scaled correctly. Okay, so what's the divergence say? You can kind of think about this as traffic. Let's say you were coming in from negative infinity. So you're going fast. That's what these big arrows tell you. You're going fast. But then you slow down. That would cause a traffic jam, right? So everything's bunching up together. That's a negative divergence. Then you get to positive y, and everyone's in that traffic jam. But then it clears up and everyone starts going faster. So then you have positive divergence because as everyone starts speeding up, they start spreading out. So that's your positive divergence. So negative divergence, think of everything bunching up. Positive divergence, think of everything spreading out. I'm going to give you one more example that's a little more complicated to calculate, but difficult to visualize. Okay, let's calculate this. So we take the derivative with respect to x of the x component, add that to the derivative with respect to y of the y component, add that to the derivative with respect to z of the z component, which gives us 2xy plus 2y plus y. So that's 2xy plus 3y. Now I'm going to give you a few to try yourself. And I encourage you to try to visualize it. Okay, so go ahead and find the divergence of each of these functions. And try to visualize it when you can. So the first one, we have d dx of x plus d dy of y, and there's no z component. So we just get 1 plus 1 equals 2. This one has a positive divergence of 2 everywhere. And if you were to draw this one out, you would see that you have the arrows always moving away from the origin, so that this has a positive divergence. That makes sense. This one has a positive divergence of 1 everywhere. And what you can see here is that all the divergence is coming from the function in the z hat direction. There's no divergence coming from the x hat or y hat direction. Alright, last one. So this is a function that actually has no divergence at all. And if you were to sketch this one, and I'm going to do a really quick, non-thorough sketch, you see something that looks something like this. And you can figure this out just by plugging in values. Okay, when x is 1 and y is 1, what does it look like? So this is a function that just swirls around and is not really spreading out, so it makes sense that it doesn't have any divergence. Lastly, we're going to talk about curl. So we saw in our last example here that the divergence was 0 because it's not spreading out, but we do see that it's swirling around, and curl is what's going to help us measure that. Curl is another quantity related to derivatives for vector fields. This one is a measure of how much the field is swirling around. So that's what this picture here is supposed to be showing you. And it's a 3D picture, so it's a little bit harder to follow what's going on. I do encourage you to go to the website here because they have some of these animated on the website, and it makes it a little bit easier to see what curl is. So when you think about curl, if you're thinking about the water analogy, a whirlpool, for example, would be an example of curl. If you're thinking about electric and magnetic fields, if you know that a current carrying wire creates a magnetic field that is a circle around that wire, so you can think of a current carrying wire as a source of curl in magnetic fields. So to think about how we calculate curl, we think about the del operator making a cross product with your vector field. So here, remember, it looks like a determinant when you're taking the cross product. And our first vector, but not really a vector, is the del operator. And then you have the x, y, and z components of your vector field. Okay, and you can write this out the long way in general. I prefer to just remember things this way. It's really easier than remembering some long drawn out formula, for me at least. So let's go back and look at the same fields we did before. So the first field we looked at for divergence was y squared y hat. So if we calculate the curl of that, okay, let's go ahead and write that out. So the x hat is d dy of 0, that's 0. d dz of y squared is also 0, minus y hat. Alright, d dx is 0, d dz is 0, plus z hat. d dx of y squared is 0, d dy is 0, 0. Alright, so this one is 0, and we've already drawn this function. So you can look at this vector field, and you can see that while it does spread out, it doesn't have any rotation to it. So it makes sense in this case that the curl is 0. Now I'm going to do the example that's harder to calculate, and it's definitely not easy to visualize. But I want you to have an example of how you calculate the curl when things are a little bit less simple. Okay, let's work this out. Okay, so what do we get? We get z minus 0. We get 0 minus 0. 0 minus x squared. So this simplifies down to z x hat minus x squared z hat. So by no means simple or easy to visualize, but you can see how the full calculation works out. Okay, I'm going to give you a couple to calculate yourself. I'm using the same functions we use for divergence, so you can compare the divergence and curl of the same functions. Okay, so these are the same functions we calculated the divergence for. You should be able to visualize number 1 and number 3. Number 2 is a little bit harder to visualize. Alright, give it a go. It is a bit of a pain to write these out. d dy of 0 is 0, d dz of y is 0, d dx of 0 is 0, d dz of x is also 0, d dx of y is 0, d dy of x is 0. So the curl of this function is 0. And remember, this is the function that shows the vectors always pointing away from the origin, so they're spreading out And if you look at the vector field, you don't really see any curling happening. So it makes sense that this is 0. Next one. Del dy of z is 0. Del dz of x is 0. Del dx of z is 0. Del dz of sine y is 0. Okay, this part's not going to be 0. So we are left with z hat minus sine x minus cosine y. Oh, and I realize now that my z's have been looking a little funny. When I write z's, I tend to draw a line through the center. Those aren't negative signs. Those are the lines through the center. Okay, so this one, we saw that it had divergence only from z. And this one has curl that's pointing in the z direction. So this comes down to another right-hand rule. So if you wrap your fingers around in the direction of the curl, well, what looks like the curl or the swirl, then your thumb will point in the direction of the curl vector. Last one. This one has a lot of the same 0 patterns as the last one. Minus negative. Okay, so we end up with z hat 1 plus 1. So the curl of this field is positive 2 z hat. So if you look at the very small sketch I made for this when we were calculating divergence, this function does look like it curls because it just swirls around but it doesn't spread out. And so if you wrap your fingers around, it's going around counterclockwise on the screen. And so your thumb is coming out of the screen. And that's the positive z hat direction. Okay, now what's really exciting is that now that we've gone over all of this, we can look at Maxwell's equations and make some sense of them. Okay, so you know all the mathematical operations in this one now, so let me just tell you what all the symbols stand for. So E is for electric field, I'm sure you know. Rho is for electric charge density, and epsilon naught is a fundamental constant. So this says the divergence of the electric field is proportional to the charge density. This is what tells you that positive charges create divergence in the electric field. Okay, so B is the magnetic field, as I'm also guessing you know. So this one says that when there's a change in your magnetic field with time, that creates curl in the electric field. This one says there is no divergence in the magnetic field. This is the one that says there are no magnetic monopoles. Alright, this one says if there is a current, well, okay, so J is current density. So it says if there's a current, that will create curl in the magnetic field. It also says if your electric field is changing with time, that will create curl in your electric field. So we have that will create curl in your magnetic field. So there's two ways to create curl in your magnetic field. And I think this is the most exciting thing about what learning what divergence and curl are, is because it lets you actually read Maxwell's equations. Now in practice, it's generally easier to use and more practical to use the integral form of Maxwell's equations. And we'll get to that next week. But at least now you can read this very famous form of Maxwell's equations. Alright, let me know if you have any comments or questions in the problem solving discussion, and I'll see you next week.